think you're on mute there.
We are now streaming the session. And
Ignacio, can you please make me a co-host so I can share the slide?
yes.
I think you're on mute there.
We are now streaming the session. And can you share now the screen, Jennifer? Okay. I will also record the session. So start recording. Well, I think we can start. Probably some people will enter into the session. Hello everyone, and welcome to the 10th session of the ISRM Young Members series. My name is Ignacio Perez. Jennifer Day from Queen's University and I from the University of Vigo in Spain. Sorry, Jennifer from Queen's University in Canada. As part of the ISRM Young Members group, are happy to chair this 10th monthly seminar. It is a great pleasure for us to be here today, and we would like to thank first all of you for attending this 10th session. Before starting, we would like to thank the support from the International Society for Rock Mechanics and Rock Engineering, and especially to Sevda Decoda, the ISRM Vice President for Australasia and Chair of this ISRM Young Members Committee. We also would like to thank to all young member representatives from a diverse number of national groups that have joined this initiative, from Spain, from Australia, New Zealand, Japan, China, Chile, and Canada, among others. And finally, we would like to thank our speakers, Dr. Jon Just Urratia from Spain and Dr. Jonathan Aubertin from Canada, for agreeing to present their work in this session. Well, before our speakers begin, we will take a moment to present key information about the seminar series. The project of the ISRM monthly seminars attempts to promote the community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and the academia, and to strengthen relations between different countries. We would like to invite a variety of young members to participate in this seminar series, and the criteria for the speakers are as follows. The first one is to be an ISRM member. You can do it through the national groups of the different countries. Have a maximum age of 35 years or 40 years if a PhD degree was obtained in the previous 5 years, and have worked in rock mechanics and rock engineering for a period no longer than 10 years. Well, the nominations of the speakers can be made by the nominees' national group or by some other person or organization acquainted with the nominee's work. And we also accept self-nominations. The nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. And on the screen, you can see our contact email. And well, this webinar is now being held every month, and we invite you all to keep in touch. So we will now begin the first seminar of the day, and I'll give some comments on the organization of the seminar. Each presentation will last 20 minutes and will be followed by 10 minutes of questions and answers. And for the smooth running of the seminar, I'll ask you to keep your cameras turned off and microphones during the presentation of the speakers. And if you have any questions, please, you can use the chat or the raise hand feature. Okay, so let's move on with the first speaker. The first speaker is Dr. Jon Just Urratia, who holds, I'll give some lines on the CV, holds a PhD in civil engineering by the University of Cantabria in Spain, and his research field is focused on rock fracture mechanics, in particular on the application of local criteria for the fracture assessment of rocks under different loading and temperature conditions. This research is performed within the Department of Ground and Materials Science and Engineering of the University of Cantabria in Spain, in collaboration with the TU Berg Academy Freiberg in Germany. And Jon currently works at Sener Enginería Systems, a Spanish company, and collaborates with the University of Cantabria in the publication of scientific articles. He has published more than 20 papers in prestigious journals and international conferences and received several awards such as the SEMR, the Spanish National Group of the ISRM Prize in the field of rock mechanics, or the PhD Extraordinary Award by the University of Cantabria in the category of engineering and architecture. And today, he will be presenting a talk entitled Application of Recent Fracture Mechanics Criteria to Notched Rock Fracture Analysis. So after this amazing CV, Dr. Justo, the floor is yours, so you can start your presentation.
Okay, thank you. Well, hello everyone. Thank you for coming, and thank you, Ignacio, for your introduction. Let me also thank the International Society of Rock Mechanics for giving young engineers and researchers the opportunity to take part in these kind of seminars. And well, let me share my screen before I start. Okay, can you see the slides? Yes, okay. So, well, as Ignacio told you, today I'm going to talk about rock fracture mechanics. In particular, I'm going to focus my presentation on the application of two recent fracture mechanics criteria to perform fracture analysis of notched rock components. These two criteria are called the theory of critical distances and the strain energy density criterion. Well, I will describe them later. I just wanted to tell you the names right now. What we aim with this study is to investigate their applicability in the field of rock mechanics, not only at room temperature, but also at higher temperatures up to 250 Celsius degrees, which is a common range in geothermal energy sources, for example, or even in nuclear waste disposal projects, for example. So just to explain the framework of this research, this is part of my PhD thesis entitled Fracture Assessment of Notched Rocks under different loading and temperature conditions and using local criteria, which I performed at the University of Cantabria in collaboration with the Technical University Academy of Freiberg in Germany. And well, Jorge Castro and César Sagaceta were the directors of this research, which was funded by the Ministry of Economy and Competitiveness of the Spanish government, by the European Regional Development Funds, and also by the Regional Fund of the Government of Cantabria. So this is the general outline I'm going to follow during my presentation. First, I will start with a brief introduction explaining some basic concepts of fracture mechanics. Then I will explain the theoretical background of the two studied local fracture criteria, which, as I said, are called the theory of critical distances and the strain energy density criterion. The former one is a local fracture criterion based on a stress field around a certain defect, and the second one is an energy-based approach. The application of these two methods requires the characterization of some basic mechanical properties of the studied materials, in this case of the rocks. So in the next point, I will describe the analyzed materials and the performed laboratory campaign. And finally, I will finish with with the main results and their discussion and some final conclusions. Okay, so let's move directly into the introduction. One of the main aspects characterizing a rock from a mechanical point of view is the predominantly fracture behavior. Quasi-brittle materials like rocks display very limited non-linear behavior before failure, and therefore crack propagation is unstable and leads to sudden fast fracture. This condition can result in catastrophic failures of rock masses or rock structures, for example, especially under the presence of defects which act as stress concentrators. So for this reason, predicting failure is a major issue of interest in many rock engineering applications, such as civil engineering, mining, or energy engineering, for example. And consequently, there is a general demand for the development and validation of new tools and methodologies that allow the analysis and prediction of rock fracture in a precise and, of course, if possible, also in a simple way. So while talking about defects, it's important to distinguish between crack-type defects, those with a theoretical null radius as those represented on the left of the slide, and notch-type defects, those with a finite radius as those represented on the right in the slide. So both of them generate stress concentrations around the defects when subjected to external loading, leading to the initiation the initiation and propagation of the cracks, right? So if we represent the stress field in the bisector plane of the defects, we can observe that the notch-type defects generate less demanding stress fields than crack-type defects. This is a simplification, but this is what is called the notch effect. So proceeding on the assumption that all defects behave as crack-type defects as proposed by traditional fracture mechanics might be very conservative in many practical situations. Well, another concept that I would like to keep you in mind is the failure modes. 3 different failure modes are generally distinguished in fracture mechanics. The first one, the mode 1, stands for the opening or tensile situation. Mode 2 corresponds to in-plane shear, and mode 3 corresponds to out-of-plane shear. Well, it is widely accepted that crack propagation phenomena in rocks are mainly dominated by tensile or opening loading modes, that is mode 1. So in this work, in this presentation, I'm going to focus on mode 1 loading conditions because of the line limitation, but in our research, we also analyzed mixed mode 1+2 conditions, okay? So the next point is the description of the study methodologies. I think it's not worth going deep into the analytical background of these methods. If you are interested, you can always contact me or have a look at the published articles. But I think it's more important to explain the basic concepts behind these 2 methods. So I will focus on the basics of them. I will not include too many formulas. So let's start with the theory of critical distances. As I said before, it's a stress-based local fracture criterion. Despite its potential and application in many materials, scarce work can be found on the application of this method in the particular field of rock mechanics. The theory of critical distances is indeed a group of methods with some common features, as the use of a material characteristic parameter with length units, which is called the critical distance, and the use of linear elastic analysis for fracture assessment. The theory of critical distances can be applied by the point method, using the line method, the area method, or the volume method, depending on how the stresses are evaluated. So the first one, the point method, is the simplest form of the theory of critical distances, as it states that fracture occurs when the stress at a certain distance from the notch tip, which is equal to the critical distance divided by 2, reaches the inherent strength of the material. There on the right of the slide, you have the analytical expression for the critical distance, which only depends on the fracture toughness and on the inherent strength of the material. In the case of rocks or quasi-brittle materials, the inherent strength can be assumed to be roughly equal to the tensile strength of the material. So in order to define this parameter, we only need the definition of the fracture toughness and the tensile strength of the rock. The second one, the line method, states that fracture occurs when the average stress over a certain distance from the notch tip, which in this case is 2 times the critical distance, reaches the inherent strength again. So in this case, instead of analyzing the stress at a certain distance, we need to analyze the stress average over a certain distance. Well, the expression for the critical distance is the same. So finally, we have the area method and the volume method. Their application is not that easy, it's not straightforward, but basically what they do is to analyze the stresses over a certain area in the first case, or over a certain volume in this case of the volume method. So moving now to the strain energy density criterion. This is an energy-based local fracture criterion, and basically this fracture criterion states that fracture occurs when the strain energy density average of a certain control volume reaches a critical value. The strain energy density can be defined as the area under the tensile strain curve. So assuming a perfectly linear behavior of rock, the critical value of the strain energy density can be defined as the area defined by the triangle. Yes, well, under the area defined by the triangle, which is defined by the tensile strength and the Young modulus in this case. In general, rocks are assumed to present a roughly linear behavior, but in any case, it should be expected to obtain a lower value of the critical strain energy density than that calculated from the real tensile stress strength curve. So in this case, apart from the tensile strength, we also need the formational parameters of the rocks. So we have to define both the Young modulus and also the Poisson ratio. This strain energy density is average over a control volume that in the case of plane strain conditions becomes a control area that's represented on the right of the slide. So what we have to do is to average the strain energy density in this area, and when this value reaches a critical value, so fracture will occur according to this criterion. Okay, so both the theory of critical distances and the strain energy density criterion, both of them assume a linear elastic fracture behavior of the rocks. When considering linear elastic behavior, we are assuming that the stresses in front of the defects vary as smoothly as in the case of the left plot. But we know that rocks, of course, are not a continuous material, so probably the stepped curve on the right could be more realistic. In any case, neither the theory of critical distances or the strain energy density criterion consider the maximum stress just at the notch tip, but they evaluate the stresses. Well, they evaluate what is happening in front of the defect tip, not only at the tip. So these conditions somehow absorbs the difference between the smooth and the stepped curves. The application of these two methods, the theory of critical distances and the strain energy density, requires the definition of some mechanical parameters of the analyzed materials. The theory of critical distances, we saw that requires the definition of the fracture toughness and the tensile strength. And in the case of the strain energy density criterion, we also need to define the Young modulus and the Poisson ratio. For this, well, consequently, in this section, I will describe the analyzed rocks and the performed laboratory campaign. So moving into the analyzed materials, we have studied 4 different types of rocks, namely a Floresta sandstone from Lleida in Spain, a Moleanos limestone from Portugal, the Macael marble from Almeria, also in Spain, and the Carrara marble from Italy. Well, among their properties, I would just like to highlight the porosity, which is around 16% in the case of the Floresta sandstone and 6% in the case of the Moleanos limestone. And of course, there is no porosity in the case of the marbles. From a microstructural point of view, the main difference between these two marbles is the grain size, the crystal size, which is relatively larger in the case of the Macael marble. Well, for the characterization of these parameters, of the required parameters, almost 900 4-point bending tests have been performed, which provide pure mode 1 loading conditions. 300 Brazilian tests have been performed, and finally 120 uniaxial compression tests with strain measurements have been performed. So first, the 4-point bending tests have been performed at different temperatures from 23 to 250 Celsius degrees, with a repetitiveness of 6 to 12 tests in some cases for verification purposes. There you have some pictures of the used samples, which consist of 180 times 30 times 30 millimeter size single edge notch beam specimens with variable notch radius from 0.15 up to 15 millimeters. Those samples with the smallest notch radius, those with 0.15 millimeters, were used to calculate the value of the fracture toughness, and the rest of samples were only used for the interpretation according to the theory of critical distances and the strain energy density criterion to compare the experimentally obtained failure loads with those of the fracture predictions. So yeah, well, here you have some pictures of the performed test. In order to define the tensile strength of the rocks, 300 Brazilian tests have also been performed at different temperatures, again, from 23 to 250 Celsius degrees. In this case, using diameter disc specimens with 64 millimeter diameter and 32 millimeter thickness. And the same for the uniaxial compression test. Again, perform at different temperatures up to 250 Celsius degrees. And well, in this case, as we needed the deformational parameters, well, we had to use special strain gauges to measure both the Young modulus and the Poisson ratio at high temperatures, which was not an easy task. Probably was the most difficult part of this experimental campaign, because these strain gauges were quite well sensitive. So let's move now to the results under discussion, which is probably the most interesting part for you. So this first slide shows the variation of the tensile strength with temperature. I have assigned a different color to each rock for a better visualization of the results. It can be observed that the tensile strength of the Moleanos limestone, for example, increases up to 150 Celsius degrees, and then slightly decreases. The Floresta sandstone also shows a slight increase in trend with temperature. However, both marbles present a reduction of the tensile strength from the onset of the heating process. These behaviors are related to two different micromechanisms. In the case of the porous rocks, the Floresta sandstone and the Moleanos limestone, the tensile strength increases for moderate temperatures due to the partial closure of pores or other pre-existing or other persisting microcracks. And once a certain critical temperature is reached, thermally induced new microcracks arise, and as a consequence, the strength is, well, there is a strength reduction, yes. That's why in the case of the non-porous rocks, the marbles, as there is no internal space for the expansion of the crystals, the tensile strength is reduced from the onset of the heating process. This other plot represents the variation of the fracture toughness with temperature, and well, relatively similar trends as those observed in the tensile strength are seen. Both the Floresta sandstone and the Moleanos limestone, those rocks with porosity present an increase of the fracture toughness with temperature, while the two marbles present a decrease from 70 Celsius degrees onwards. Here we have some representative stress strain curves obtained from the uniaxial compression test for each of the 4 selected rocks. Well, they offer a clear view of the linearity of their behavior, even at different temperatures. The Floresta sandstone and the Moleanos limestone present a very linear behavior even at 250 Celsius degrees. The Macael marble also presents quite a linear behavior up to 70 degrees and less linear behavior for higher temperatures. And finally, of course, the Carrara marble does not present a linear behavior even at room temperature. Consequently, worse fracture predictions are expected for this material. These plots represent the variation of the apparent fracture toughness with the notch radius. So it somehow represents the existing notch effect. Its dot corresponds to the values of each of the performed individual 4-point bending test. And the notch effect is interpreted in this case according to the theory of critical distances and well, in particular to the line method. Well, yes, in particular to the dashed lines represent the calculated curve according to the line method, and well, we can see a good agreement between both of the curves. Similar results are obtained also at higher temperatures. These are the results for 250 Celsius degrees. And we can observe that the trends are kept roughly the same, which indicates that there is no strong influence of temperature on the notch effect. And finally, well, these are the fracture prediction results for each of the analyzed rocks. In this case, for the theory of critical distances, and in particular for the line method. In any case, very similar results are obtained with the point method. The vertical axis of the plots represent the ratio between the predicted failure load and the experimentally obtained failure loads, and the horizontal axis represent the notch radius in all the cases. Dots indicates the prediction of the individual test, and the solid lines the mean predictions. And while the first row corresponds to the results performed at 23 Celsius degrees, and the second row represents those results of 250 Celsius degrees. We can consider relatively reasonable fracture predictions in general within a strip of plus minus 20% in all the cases. Well, the Carrara marble, of course, is the exception, as expected from the non-linear behavior, even at room temperature. And well, these are the same results for the case of the strain energy density criterion. We also obtain relatively accurate predictions in all the cases, except for the Carrara marble. If we compare both results, in this case, these are the results for 23 Celsius degrees. If we compare, we can see relatively similar results of both methods. The dashed lines correspond to the theory of critical distances, and the solid lines represent the strain energy density criterion fracture predictions. We can observe that the strain energy density criterion tends to slightly underestimate the failure load compared to the theory of critical distances. And another drawback of this method is that it requires the deformational parameters, while the theory of critical distances only requires the fracture toughness and the tensile strength. So yes, well, just to finish, I have included a slide with a list of published articles dealing with the application of both methods, both the theory of critical distances and the strain energy density criterion. Well, just in case you are interested. And just to finish, well, I would like to highlight that the fracture behavior is influenced by thermal induced micromechanisms. We saw that both the tensile strength and the fracture toughness increase up to a certain critical temperature in the case of porous rocks, while it decreases from the onset of the heating process in the case of non-porous rocks. We also saw that the notch effect was evident and significant in the experimental results. It was observed how the apparent fracture toughness increases with the notch radius from a certain notch size. From a certain notch size. Well, it's important to highlight also that both the theory of critical distances and the strain energy density criterion offer reasonable and similar fracture load predictions within a range of plus minus 20%. This strip is quite common in fracture mechanics to consider the accuracy of any criterion. So they were valid even at temperatures up to 250 Celsius degrees, as long as linear behavior was observed. So they both offer two easy to use tools for accurate predictions and evaluations. In fact, the first one, the theory of critical distances. In this case, once the critical distance is defined, it is straightforward to apply the theory. It is straightforward to apply this method, and only two parameters are needed: the tensile strength and the fracture toughness. And in the case of the strain energy density criterion, well, additional tests are needed, in particular, uniaxial compression test to define the deformational parameters, both the Young modulus and the Poisson ratio, which are not easy to obtain because you need special strain gauges, special cables that can work at those temperatures, and well, special adhesives. Also, the welding must be able to work at those conditions. So, well, that was all, and thank you for your attention. And if you have any question, I'm happy to answer them in case I know the answers.
Okay, thank you very much, Dr. Justo, for your interesting presentation and for sticking to the time. Now we have some time for questions, if any. So does anyone have any questions from the audience? You can use the chat or...
Okay.
Hi, John. I read some of your articles, or one of two. They are very interesting stuff. Great presentation. Thank you very much.
Thank you.
I just have a question. You say that the temperature didn't affect the results in the notch. Okay, so Barani.
In the notch effect, yes. In
Exactly.
The absolute values of the fracture toughness, it does have an influence, but in the notch effect, we did not observe any particular, any clear trend.
Okay, so Barani was doing some tests on Wembeyan marble. So he discovered that when you heated marble, for example, the cohesion, the intergrain cohesion practically disappeared. So I always have in my mind that if you heat marble,
yes,
something should happen. So what do you think that the temperature didn't affect the results you were presenting?
Well, let me go in the slide to those. Well, yes, okay. Well, these were the results of the variation of the apparent fracture toughness with the notch radius. In the case of the marbles, as you can see, there is, for example, in the Macal marble, there is a lot relatively high scatter of the individual results. But in any case, the calculated curve according to the line method and that of the best fit curve have a good agreement. But in the case of the marble, no special trend was observed. If we compare these results to those at 250 degrees, the trends were observed to be relatively similar. It's difficult to obtain robust conclusions because of the high scatter we have. The Carrara marble has always give us relatively bad results in all the tests because of its nonlinear behavior. So we couldn't obtain any deep conclusion on this issue. In any case, of course, it's an interesting question, and I will have a look at it because, of course, especially in the marbles which have no internal space for the expansion of the crystals, there must be effect. Yeah.
Thank you.
Any questions?
Maybe someone is writing on the chat. I don't know how to check that.
I'm reading the chat, but we have no more questions. So
okay.
Only one comment, if I could. I'm
comment.
Jorge Castro.
Yes.
No, regarding the question of Dilberto, that fracture toughness, indeed, it decreased with the temperature. So for 250 degrees, that fracture toughness was lower than for 23 degrees. What it was similar was the influence of the notch effect, but the fracture toughness decreased with the increase in the temperature.
Yes, of course. The absolute value here we have the fracture toughness. This is the tensile strength. The fracture toughness in the case of the marbles, the blue line and the green line. Well, from 23 to 70 Celsius degrees, it was almost constant, but then we can see a clear reduction of the values.
okay. So I just have a little curiosity. Have you tried to compare the results with the tensile strength results obtained in the study? Fracture toughness results compared with tensile strength results?
Yes, well, I don't have the results here because I'm not working in my computer,
Yeah, it was just a
but yes, we are writing. Well, I think it's now under revision. A technical note on the comparison of the tensile and the fracture toughness. Yes, maybe Jorge Castro can tell you something about this. He's connected.
Well, no, just to comment that, yeah, we saw in the literature that there were some empirical correlations between the fracture toughness and the tensile strength. And there is a ratio that varies between two values. And we understand that somehow that ratio for us is, for example, related to the critical distance or to the area that we average for the strain energy density method for the area that we average the energy. And that is in turn related with the grain size. So the ratio between the direct tensile strength and the fracture toughness, that ratio is more or less constant, but it somehow depends on the grain size. For rocks with higher grain size, the ratio has some values, and for lower grain sizes, the ratio varies a little bit. There are also, I think in the literature, there are also some numerical simulations that propose some correlations in that sense.
Okay, many thanks. I'll look forward to reading your paper because I think it's a very interesting topic and recent topic to be studied. So, well, thanks for your answers. And now I switch the role to Jennifer Day, who will continue with the seminar. If any
Thank you.
Excellent. Thank you, Ignacio. Thank you, John, for your presentation, and everybody for your questions. So let me introduce the next speaker of the webinar session. Our next presenter is Dr. Jonathan Aubertin, who holds a mining engineering degree from McGill University in Montreal, Canada. From 2012 to 2021, he held various roles within mining company Windsor Salt and the US parent company Morton Salt, working as a mine engineer, production engineer, and general supervisor. Jonathan completed a PhD in geological engineering in 2020 while working at the Weeks Island mine in southern Louisiana in the United States. In 2021, Jonathan transitioned to an academic role as an assistant professor at École de Technologie Supérieure in Montreal, Canada. His research work focuses on rock blastability, rock mass characterization, and time dependency in rock engineering. Today, he will be presenting a talk entitled Differentiating Cratering Mechanisms in Rock Blasting based on Geomechanical Characterization. So I'll pass it over to Dr. Aubertin.
Thank you very much, Jen. Can you see my screen?
Sure can.
Excellent. Thank you very much. Good morning, good afternoon, good evening, depending on where you're at in the world. I'm very proud and honored to be here this morning. My talk, as Jen mentioned, is about differentiating cratering mechanisms in rock blasting based on geomechanical characterization. My name is Jonathan Aubertin. I'm a professor at the École de Technologie Supérieure in Montreal. The presentation I'm talking today is about rock blasting, which is a special field of rock engineering, which is, it might have been very interesting because it relates a lot of practical applications with some more theoretical notions pertaining to rock mechanics and rock fractures. The presentation will go as follows. I'll start by putting a brief overview of what rock blasting is all about, giving you a context of what it's applied to. I'll talk about rock mechanics and rock blasting and related to some cratering fundamentals. Then I'll delve into some of the mechanisms behind traditional cratering and talk about some not so traditional aspects of cratering and fracture mechanics associated with blasting. The overall goal of this presentation is to drive towards geomechanical differentiation, basically talking about different geologies and how it affects the actual cratering mechanism taking place during the blasting. I think we're all very familiar with rock blasting. It is a common process in the construction industry and the mining industry. It's very prevalent in surface mining and underground as well. We see it a lot. You'll see it a lot for developing underground tunneling operation, developing large-scale infrastructures underground. And it is something that you see a lot as well to define rock slopes around railway infrastructures, roadways. It is something very common in many different fields. Ultimately, it's important to realize that rock blasting remains today the most cost-effective means of loosening and extracting rock. And so it's something that we do a lot. There's some very good reasons to improve how we understand how we do rock blasting. Efficient rock blasting leads to obviously lower consumable costs. If you've got efficient rock blasting, you just cost less in terms of consumable. You can also optimize your fragmentation, which is very important in anything pertaining to mineral processing, especially for ore treatments. You can get a much better recovery or control in terms of the geometry of what you're blasting. Very importantly also, and that's something that is a growing field of interest with respect to rock blasting, a more efficient rock blasting process leads to a much lower environmental footprint, both in terms of energy consumption downstream, but also just in terms of gases generated by the blast and runoff associated with it. There's some fundamental notions that I think need to be discussed when we think about rock blasting, especially when we try to relate this to rock engineering and how both correlate to one another. The process of blasting involves a solid, a liquid, or a slurry that is transformed by a detonation chemical reaction from its original state into a gas in a very rapid fashion. This is imparting a shock wave to the rock surface near the blast hole. Now, very close to this blast hole, you have a very, very high pressure being imparted. You're basically crushing, pulverizing the material. Then further along, you have this transitional zone that is not quite pulverized, which has a bunch of radial fractures, but is still highly damaged. Then you have a zone that is more important for all the practical application of blasting, which is the fractured zone where you have a series of radial fractures emanating from the blast hole section. This fragmentation zone, this radial fractures, is not particularly large. You're not destroying the rock mass, and it's not the primary means of fracturing for extraction, but it's very important from what takes place downstream. Past this damage zone, what you have is the propagation of an elastic wave. Basically, you've damaged the rock mass near the blast hole, you've generated a series of radial fractures. Then past this, you have elastic transmission and propagation of pressure waves. The primary pressure wave that we usually talk about is P wave, compressive wave. That's usually the driving shock wave that is of interest for blasting. You have all the other types of of seismic waves that we're used to, especially shear wave whenever you interact with some heterogeneous components, some fractures, some local inconsistency. But P wave is typically the driving factor of interest. Now that we acknowledge what's going on around the blast hole and how this shock wave is transferred elastically to rock mass, it's important to question how we actually fracturing this. It's not because we're pulverizing along the blast hole that we've extracted several thousand tons of rock. So there are three distinct cratering mechanisms responsible for actual rock fragmentation and extraction for practical application considerations. The first and foremost one that is most detailed in literature is radial fracture propagation. This P wave, this compressive wave emanating from the blast zone, travels radially away from the blast zone and is reflected in tension by any given free surface. Typically in blasting, you have this big bench face in a mine or in a underground would be cut in the middle of the face. You have this free surface that reflects the wave in tension. This wave intention comes back towards the blastole and interact with the radial fractures I talked about previously. The tensile wave basically opens up and props up those fractures, which allows those fractures to reach all the way to the free face. This behavior is very critical to how the cratering process takes place, because the geometry of radial fractures and the way they expand reaching the free surface yields a generally almost prismatic crater shape. And this prismatic, this triangular cross-section of the crater is very fundamental to all modern notions of blast designs, and all our guidelines and rule of thumbs are related to some extent to that kind of dimensioning of the crater. A second cratering mechanism, which is important but probably not as prevalent because of the geometry of the process, is spalling, which is basically failure in tension. When you have this tensile wave being reflected at the free surface, you have failure in tension if you're close enough to that free surface. The notion associated with this failure in tension is that you need to be at a short enough distance between the blastole and the free surface for it to actually take place. Otherwise, there cannot be any kind of failure associated with this. So it's something that does take place to some extent, but is not prevalent because the geometry needs to be special. This spalling criterion, this spalling feature would typically take place or be used in more specific special blasting conditions, such as perimeter blasting, where you need something almost parallel to the free surface to have a nice smooth wall. The concept of spalling is also used in more laboratory scale testing, where you want to know the dynamic tensile strength of rock. The samples you have here on the right were tested with a small shock wave at the bottom of the rock rod. The wave reflected at the tip comes back in tension and fractures this rod at a certain place, and the position of this rod, knowing the elastic properties of that rod, allows you to determine its tensile strength. So it's very characteristic. We know it's there, but it's not quite prevalent in large-scale production operation. The third cratering mechanism, which is quite important, is the concept of wave interaction. When you have this wave propagating compression being reflected in tension at the face, you basically have this tension wave being reflected, the end of it interaction with the tail end of the still incoming compressive wave of the original emission. So you basically have this compression wave, which is acting as a very high compressive stress component. We'll call it sigma 1. And if you have any kind of incidence with the reflected tensile wave that is not head on, you have angle of incidence between sigma 1 being very high and compressed and sigma 3 almost perpendicular, which is coming backwards and basically negative. So now you have a situation, sigma 1 very high, sigma 3 negative. You have a very high deviatoric stress, localized very high deviatoric stress. And as we can see on the figure on the right, which is a simple analytical representation of this situation, what you get if you map the high point of this deviatoric stress is an elliptical profile, which is very characteristic of this cratering behavior. So now that we've defined the cratering mechanisms behind rock blasting, the next question becomes, which ones are more prevalent? When is one cratering mechanism taking place and why? And how is geomechanics taking place? The way we've been doing our research to quantify and define this has been through the use of single hole blast testing. We're basically shooting an individual blast hole, measuring the resulting crater, varying the distance between the blast hole and the free surface, which we're referred to as the burden. We vary this dimension and we try to quantify the resulting relationship. The crater on the left is a simplistic representation, but what we try to do from this testing is to calibrate a power formulation shown on the right, which allows us to index the behavior of the cratering in the rock itself. You get two parameters, namely psi and epsilon star, that define how your rock mass is behaving in terms of blasting. And one of the interesting and useful piece of this formulation is that the exponent there, epsilon star, actually defines the cratering mechanism taking place. If you have the exponent lower than 1, you have concave cratering behavior taking place. If you're above 1, you have some convex cratering, which may not be intuitive, but it's something that's been observed and we'll talk about later. Then if your exponent is equal to unity, then you have prismatic cratering, which is associated with this traditional, more accepted, acknowledged cratering behavior, which is representative of typical rules of thumbs and guidelines. To further investigate this and to use this approach of single hole blast testing, we did a bunch of different tests in various geologies. We did some some testing in various hard rocks and also on concrete blocks, and those various testing have been published in different places. But what we've noticed by representing the result through this formulation proposed is something very consistent. The advantage of having modern topographical mapping tools like LiDAR is that you're no longer trying to best fit one value to a given crater. You can measure the crater profile at different interval along the blastable axis. And so what we see from those given hard rock testing is, from a general standpoint, hard rock, you get a constant exponent value regardless of the burden, the evolving burden, up to a certain point. That exponent usually revolves around 1, which is what we typically expect from hard rock blasting. We expect that prismatic cratering. Then at some point, you have a tipping point going up where past this, you start having a higher value of the exponents with a higher burn value. We'll get back to this in an instant, but to sum this up, for the most part, in hard rock, the exponent is constant and close to unity. By contrast, we did a lot of work, and actually a lot of my work was originally in salt and to some extent in potash. We've seen this consistent recurring elliptical cratering profile in all those underground salt mines. And you can see this, we've done this in tabular deposits, in heterogeneous salt deposits, and pure domal salt. And we consistently get this concave cratering, elliptical cratering profile, which we associate with the exponent being lower than 1. So why are we seeing these differences? We understand there's existing cratering mechanisms. We clearly see a differentiation between what we expect as soft rock, salt, potash, and similar lower strength materials, and you have those hard rock material that are prismatic. So we first investigated elliptical cratering, wave interaction. Why are we not seeing this? Well, what we found from numerical modeling using LS-DYNA software, which is a generally accepted software for these kinds of simulation, is that elastically speaking, the interaction process, the wave interaction does happen. The wave takes place, there is higher deviatoric stress in an elliptical shape, but the material strength dynamic of hard rock, generally speaking, is so high that even though you have higher localized hotspot of high deviatoric stress, you actually never reach a deviatoric stress high enough to fracture the rock. And so the only way to actually fracture it and remove a crater is through radial fracturing, because that slower spot that's propagating a radial fracture towards a free surface. By contrast, soft rock, salt, and potash, which have been documented to be the way we talked about this, if you simulate the same blasting conditions, same type of explosive diameter, and etc., now you're getting a situation where you have deviatoric stresses that are at or above the mechanical strength of material. And there's some circumstantial advantageous situations, such as a different type of explosives used in those materials. But bottom line, you get a situation in those types of rock where it is possible to have wave interaction, whereas in hard rock, it's not possible. Hence, from a general standpoint, in soft rock, you have wave interaction cratering yielding elliptical cratering. In the hard rock, you have the generally acknowledged radial fracture cratering open. We've talked about convex cratering very briefly early on. I think it's important to get back to this because there's always going to be other types of non-conventional rock breakup types. There was a very interesting study performed by Dr. Wimmer on critical burden experiments. He basically did single hole blast testing the way we did, but pitched the blast hole very steep in the rock to increase progressively the burden and really evaluate the evolution and the impact of burden. And as you can see, as you get closer to this critical burden, as you get close to a value where a burden where the rock just won't blow up, won't crater up, you get the seemingly convex behavior, which is what we kind of not necessarily expect, but has been seen for critical burden, and we can quantify with the formulation previously proposed. Dr. Wimmer was kind enough to share his data set. A lot of this was topographically maps after the blasting situation, and he was kind enough to share this data sets we were able to review and analyze. And what we saw was a mix of both of what we've seen before and what we've talked about and what was talked about in terms of critical burden. What we see at the small burden range, we see this characteristic almost circular shape, which we talked about this. It makes sense. You're close, you have a small burden, you're close in the face. You expect something somehow circular because you're in the spalling range, which you get at small burden. Here at the center, which this is just one cross section along the crater, but it's actually the typical range in practical operations and production, you get the seemingly prismatic cratering, which we expect from hard rock blasting. What's interesting when you get closer to the critical burden now is this seemingly convex shape, especially the crater on the right, which we really see something going on here, opening up in a convex shape. Now, what's very interesting to note is going back and reflecting on the mechanisms taking place, you have a combination of two different set of cratering mechanisms. You still have radial fractures propagating, interacting with the tensile zone, but you also have this localized shallow spalling taking place. Now, if you don't have something dominant, such as a radial fracture precluding everything else, you have this opportunity to see the interaction of both. And so while we describe it as convex cratering, which makes it very convenient for quantifying and modeling purposes, what we actually see is a combination of two different cratering mechanisms, namely radial fracturing combined with spalling, that yields this larger than one exponent and convex crater. So in concluding remarks, there's, as I described, three coexisting cratering mechanisms: spalling, wave interaction, and the traditionally well-acknowledged radial fracture, which is prevalent in hard rock. Wave interaction, elliptical cratering, arises more specifically with soft rock. You need to have a special geology to allow you to get to such type of cratering. Then you have radial fracture, which, as I mentioned, is prevalent in hard rock. It's the basis of rock blasting designs as we know it in modern textbooks. And the reason you don't see wave interaction cratering is because there's no local failure initiation, despite having this spike in deviatoric stresses. Then you have convex cratering, which is a combination of radial fracture and spalling, which yields two different combination of crater shapes. In practice, it's important to acknowledge what we're doing this for. We're trying to quantify the shape of the crater with respect to the burden. And this is a good example of how we use this, how it's important to quantify, to calibrate your single hole blast testing site specific. At this baseline, we were blasting things in a mine site, and we basically took the time with a can of paint and a high reach to paint every single crater, every blast hole, what the profile of the crater would be based on the burden dimension. And this is only achievable if you actually do this, your calibration with single hole blast testing. Now, this is a bit extensive. You don't need to paint this every time, but this was a very useful tool and process to showcase to the workers, to the workforce, to the collaborators that this is why you're doing this. This is why you would move a blast hole a certain place, because you can just pull more out of it and you actually get that site-specific calibration. Before I conclude, I need to acknowledge a lot of people obviously answered for supporting me as a young professor with the Discovery Grant, industrial partners, including my former employer, Morton Salt, ETS, my university, École Technologique Supérieure, and the construction engineering department, and my previous outfit, my previous brothers in arms, Queen's Geomechanics Lab, where a lot of this research was originally done. Here's a series of references, and I would be glad to hear from you guys for some questions. Thank you very much.
Excellent. Thanks very much, Jonathan, for a very interesting presentation. Now we have about 10 minutes for the question and answer session. Does anybody have any questions?
Hi,
Hopefully it
Jonathan.
Yeah, go ahead.
So how do you think that different deformation moduli due to geological structures are going to increase or decrease the magnitude of the reflected tensile wave?
That's a very good question. There was, I remember the year 2008, 2009, the Rock Medal Award was awarded to somebody that studied specifically to some extent that answer. It was a very good piece of work. Fracture, if we go just about structures in the rock mass, this joins, this continuities, like that. You have this simplistic continuum that we like to assume as engineers because it makes our life simpler, where you propagate, then you reflect. But when you have those little asperities, discontinuities, voids, every void is partially reflecting the wave and partially until it squeezes and closes because of the pressure of the wave, then it allows transmission. So, you know, while you're going to rock mass and everything is extremely fractured, and you think, well, that's going to be easy to blast. Well, it's not so easy because everything that is fractured, every little joint until it closes is actually reflecting the wave backwards and not really helping you in doing your overall process. So the short answer is when it's very fractured, you're impeding your ability to use the tensile wave reflected in the free surface. So from what we've seen, and we're investigating this numerically, and we're doing testing literally tomorrow morning on a fractured rock mass place to see how it's going to behave. Numerically speaking, what we see is that radial fracture is still taking place. It's not really imparting it. The wave comes back partially further quicker, but it still interacts with the radial crack. So it's not a big problem. Whereas wave interaction, now you need the full-blown thickness of that tensile wave reflected. So if you have partial energy being reflected ahead of time because of local asperities, joints, and voids of your rock mass, then you can't get as much of this energy being reflected by interacting at the key points to create that hotspot surface. So for radial fractures, it's a big thing because it's the joints themselves are can stop and block the fractures from propagating. But just thinking mechanistically speaking, it doesn't affect it nearly as much as wave interaction, because now you can't achieve that deviatoric stress you need for localized fractures.
Thank you.
Hassan, please go ahead.
Okay, may I go?
Yes.
Yes, please go ahead with your question.
Thank you, Dr. Aubertin, for this very impressive presentation and good work, if not excellent. Let me ask, when did the combine spalling plus radial fracture occurs? Especially, I want to ask that the spalling plus radial fracture depend on mostly rock strength, material strength, what I mean, or the rock structure or mass strength. I mean the mass strength. Okay, thank you.
Well, if for radial fracture, so if I understand correctly, so for spalling, the ability or lack thereof ability of spalling to take place is related primarily to the tensile strength of the material. And that's why you use this feature and phenomenon to do special testing designed to test where the breakage takes place along the rod. That's how you would define in laboratory settings the tensile strength, or how you can use this. For radial fracturing, a lot of this has to do with the first component I talked about in the presentation, which is the damage zone itself around the blast hole. The range of which those radial fractures initiate and propagate, their initial depth and range at which they propagate, influence a lot how much the potential for interaction with the reflected tensile wave, because the damping of that wave is exponential. It's not just a linear thing. The further away you're coming back, you're losing a lot of that energy and rapidly. So if your radial fracture is propagated far enough, you have a better chance of interacting with this. Now, the distance at which the radial fracture propagates is related to some extent to the rock mass strength. It can also be related to the structures, because the structure can help or actually be a nuisance, because those fractures can be in the way and act as a blocker. It also relates, and that's something that we've studied a lot and shown, at least in salt mines, was very important. It relates a lot to the explosives you're using, because if you're using an explosive that is using too much energy, you pulverize your rock near the blast hole, but you have very little energy left propagating in the rock mass, and you don't have that much radial fractures emanating. So you got to be mindful. To answer your question, the mechanical strength of the material is important, defining how far those radial fractures can go. Structure is important because they're going to either help you or be in the way of propagating and reflect, but also the explosive material you're using themselves define the size of that damage zone, which is extremely important to achieving the cratering you want. I hope I answered your question like that.
Thank you.
Are there any other questions for Dr. Aubertin? Okay, well, thank you for your participation in this question and answer session. So we'll move on to the closure of the webinar. Jonathan, if you wouldn't mind unsharing your screen, and we'll return with the seminar slides. So we're at the end of this 10th ISRM Young Members Seminar. On behalf of the organizing committee, I'd like to thank the ISRM for helping us in the organization of this event. I would also like to thank Dr. Jon Just Urratia and Dr. Jonathan Aubertin for their very interesting and valuable presentations that addressed two very relevant topics in rock mechanics and rock engineering. We hope this seminar provides you with new insights and new challenges for future research, and could be a periodic event for sharing ideas about rock mechanics and related topics. For this reason, we want to invite you for the next seminar that will be virtually held in the last week of November. The exact date and time are to be announced. And our speakers for that will be Alida Hartzenberg and Jean-Pierre Gouveia, who will present their works respectively on structural mechanisms contributing to large-scale hanging wall instabilities on the UG2 reef horizon, and establishing a testing criteria to relate the in-situ performance of static and dynamic capable mesh. Further information about the next event will be available in the ISRM newsletter and website and LinkedIn, so please keep in touch to not miss out on the next webinar. If you're interested in participating as a speaker in this seminar series, please feel free to contact us by email at isrm.ym.seminar@gmail.com. Thank you very much for your participation, to the speakers, questions, and audience members for taking the time to attend this webinar, and we'd like to wish you a wonderful and safe day.
Thank you, Jennifer. So we can close this seminar. Thanks from my side for your participation and for being there. And well, keep safe, and I wish you a wonderful day.
Likewise. Take care, everybody.
Bye-bye.